In this video, we'll walk through Theorem 3.24, which uses the concept of distance-preserving spanning trees, which we looked at in the last video, to prove an upper bound on the radius of a graph in terms of the order of the graph. In particular, the radius of the graph is always, or is no more than half of the number of vertices in a graph. So let's see how this works. All right, proof. We'll start by picking a central vertex. So maybe I'll type this. So let's let U be a central vertex of G, and let T be a spanning tree of G that is distance preserving from U. Now the key thing to note here is that since T is distance preserving, the radius of the tree is equal to the radius of the graph, because it preserves distances. And so it suffices, so we show that the radius of T is less than or equal to n over 2. So we'll just look at the spanning tree, the distance preserving spanning tree, and it'll suffice to show that. So let's assume to the contrary. That the eccentricity of this central vertex U is, since it's central, right, if I can show that this is, or if I assume that this is greater than or equal to n plus 1 over 2, then that will contradict the radius being at most n over 2. Now, if our order is either 1 or 2, there's really nothing to show here, and so we can say that n is at least 3. That'll help our argument make sense. Again, if it's order is 1 or 2, there's really not a whole lot to show here, and so we can just assume this. So, right, so U is a vertex in the spanning tree. It's a vertex in the graph, and so it's a cut vertex of the spanning tree. Why is this? Well, if it weren't, it would be a leaf, and its degree would just be 1, and it wouldn't be a central vertex unless the order was 1 or 2, but we're assuming the order is at least 3. So we can assume that U is, well, we're not really assuming it, we're deducing that U is a cut vertex of the spanning tree. So when I remove it, I'll end up with a forest. So here's what our situation looks like. We have U, and when I remove that, I end up with possibly several components, at least 2 components. I'm going to call this one I'll hold off on naming this one. So I'd like to say something else here. I'd like to say that, right, we're assuming the eccentricity of U is at least n plus 1 over 2. And so one of these components has to have at least n plus 1 over 2 vertices in it. That's going to be T prime. So let me make a note of that over here. 1, since eccentricity of U is greater than or equal to n plus 1 over 2. I can't type greater than or equal to. Since eccentricity of U is greater than or equal to n plus 1 over 2, there is some component with at least n plus 1 over 2 vertices. And remember, it's a connected component, hence it's a tree. So also, since I know this is tree, I know that U is adjacent to exactly one vertex over here in T prime. I'm going to call this vertex V, and this vertex is going to end up being quite special. So I'll say here, let V be the unique vertex in T prime that is adjacent to U. Right, how do I know there's a unique vertex in T prime that's adjacent to U? Well, suppose there's not. Suppose it's adjacent to two vertices. Since T prime is connected, there would be a path between V and that other vertex in T prime. And there I would have a cycle that would involve V, that other vertex, and U. So there's a unique vertex over there. And what I'd like to show here, my claim is that the eccentricity of V is less than the eccentricity of U, which is a contradiction. So if I can just establish that, I'll be done. I'll have my contradiction, and we'll have our bound on the radius. So why is this true? Well, look at any vertex W in T prime that's not V, because then it'd be 0, and that's, it doesn't really matter. So pick any vertex W in T prime. Then, well, any path from W to U has to go through V. And so for any W here, the distance from W to V is strictly less than the distance from W to U. And so we can say that the distance from W to V is strictly less than the eccentricity of U. This is going to hold for any vertex W in T prime. And then if I give myself another vertex W over here, clearly it takes a little bit longer to get to V, but this is where the bound comes in, right? There are n plus 1 over 2 vertices in T prime. And I need the total number of vertices to add up to n. So I have one vertex U. I have n plus 1 over 2 vertices in T prime. So in the rest of the graph, there are at most, n minus 3 over 2 vertices in the rest of it. N minus 3 over 2 plus n plus 1 over 2. That gives me n minus 2 over 2 plus the extra 1. That gives me n. Right, just pausing for a second here, make sure that makes sense to you. Right, yeah, let me just add it up, right? So where did I get that n minus 3 over 2 from? So let's say x, there's x many of these. So I need n to equal x plus n plus 1 over 2, at least that many. I'll assume just n plus 1 over 2 plus 1. So that's n plus 3 over 2. So I have n minus n plus 3 over 2 equal to x. So that's 2n over 2. That gives me x equal to n minus 3 over 2. So that's where that n minus 3 over 2 comes from. And so in particular, I do have that the distance for any W over here, we do have that the distance from W to U email notification. The distance from W to U is 1 less than the distance from W to V. So maybe I'll say distance from W to plus 1 is the distance from W to V. However, the distance from W to U is at most n minus 3 over 2. So the distance from W to V for any W over here is at most n minus 3 over 2 plus 1. That's n minus 1 over 2. And remember, I'm assuming the eccentricity of U is at least n plus 1 over 2, so this is less than the eccentricity of U. So the distance from W to V for any W in T prime, so this is for W in T prime, that's all less than the eccentricity of U. And then the distance from W to V, this is for W not in T prime. It's also less than the eccentricity of U, and so for all W in vertex set of G, the distance from W to V is less than eccentricity of U. Hence, U is not a central vertex. V would have less than, so eccentricity of V in T is less than the eccentricity of T in U, but that's a contradiction because I chose U to be a central vertex. And that proves it. So spanning trees can be handy. In particular, we were able to use this idea that when I removed U, I had a disconnected graph, and then I could use that property to sort of help me out here to give me more leverage. So sometimes selecting a spanning tree that's distance preserving from some vertex can be a helpful aid in a proof. All right.